Hi everyone, welcome to this video. We're going to go through some simple harmonic motion questions for A-level physics, and there's going to be a little bit of circular motion thrown in as well. So for AQA, this is paper 1, even though it's a bit of year 13 content usually, and let's dive in straight away with this question here. So in this question, we're asked for 2 marks to describe or state what is meant by simple harmonic motion. So out of all the definitions in this topic, this is the one you should know because it is basically the name of the topic itself. Now for simple harmonic motion, and the easiest situation to think about is a swing going backwards and forwards, and simple harmonic motion states, so we can say acceleration is directly proportional, made a mistake there early doors, to its displacement. Now, when we talk about that, what we mean is when we look at our equation sheet, and it's always handy to use an equation sheet for definitions if you can. We've got definition, circular motion here, we've got acceleration here, is equal to minus omega squared x. A is acceleration, x is displacement, this is a constant, so A is proportional to x. The second part of the 2 marks is for this negative sign here. When we have a negative sign in physics, it means all about direction. So you'd say in the opposite direction to it, or you could say directed towards equilibrium would be absolutely fine. The idea is if I've got positive displacement in this direction, so let's say that's positive x, acceleration is going to be going the other way, so therefore it's they're negative to each other in the equation sheet. Next one we're going to look is the frequency of the oscillations of a simple pendulum of length 984 millimeters, and we've got to give our answer to appropriate number of significant figures. So we can use the other expression which you saw in the equation sheet just there, which is for the time period of a pendulum, which is down here, and frequency is 1 over t. So if we work out t, we can then do 1 divided by that. So if t is equal to 2 pi and root L over g, we've got the length, we have to put that into meters obviously, so I've got 2 pi root, and then this is going to be 0.984, and on your equation sheet you're going to have 9.81, and then once we work that out we can then figure out what the frequency is. So the time period here is going to be 1.990 something, that's seconds, so therefore frequency equals 1 over t equals 1 over 1.99, which is going to be equal to 0.503, or it's 5025, and we're going to say 0.503 because 3 significant figures, look at our number here, this is 3 significant figures, and G is 9.81, that's 3 sig figs as well. If you're ever wondering where they would find a question to penalise you marks, it will always be obvious, like in this one it's obvious it should be to 3 sig figs, so that would be an example of one here. So the displacement from equilibrium is 42 millimeters. So let's again have a look at our equation. We're looking for acceleration. We've got a couple of equations here, but this is the main one, the one I showed you earlier, which is we're gonna be able to work out because now we have the frequency. Top tip as well, usually they ask you to follow on stuff from questions. So which can do A equals minus, and then 2 pi F is the expression for omega squared times by displacement. So putting these numbers in, so 2 pi and F we've just worked out, you get error code forward if you didn't from earlier, so I'm going to say 503, all squared times by the displacement, that's obviously got to be in meters, so we divide by 1,000, and if we put that into our calculator, we get about 0.42 or 0.419 meters per second squared. Next question is a really interesting question. It talks about intervals. We're talking about a pendulum of time period 1.9 seconds is set up alongside another pendulum of time period 2 seconds. They're displaced in the same direction and released at the same time. Calculate the time interval until they move in phase. So this one you kind of got to imagine it. So I'm going to do it with pens. Imagine you've got 2 pendulums. If they've got the same time period, they'll move together like this in phase with each other. If one of them lags the other one slightly, the idea is that one will take a little bit quicker, so that actually over a period of time they'll suddenly start moving not in phase, and then eventually they'll start moving in phase again. So we've got to figure out how long it will take for that to happen. So basically if we look at how many lots of this oscillations there are in this oscillation, that will help us out. Okay, so one approach for this question, it'd be kind of like in GCSE maths where you're asked to find like a lower lowest common multiple. There we go, I was going to say factor then. Lowest common multiple. So basically at what point after how many oscillations will those be equal to each other? So if you know there's 0.1 difference and the whole one is 20, sorry, this one's going to be 19 oscillations, and this one up here is going to be after 20 oscillations. So if you don't want to take my word for it, do a bit of trial and error if you're not sure about how to start that one off. But if I do 1.9 times 20, that's going to be 38. And if I do 2.0 times 19, that's obviously going to be 38 as well. So after 38 seconds, so you could say something like after 38 seconds, and then we say this one has undergone 19, this one has undergone 20 oscillations. After 8 seconds, that's when they are back in phase. The other marks in this question are just for basically what we said. So something like, 22.0 seconds times 19 equals 38. And then 1.9 seconds times 20 equals 38. There are other different ways you explain it using the mark scheme. I'll show you the mark scheme quickly here. So a lot of different ways you could express it. You could do the time interval and then do n equals 2 divide by 0.1, so work that out. But as long as you work these things out here and have a final answer, so after 38 seconds, they're in phase. So they're one oscillation different at that point. Different, we could say 2 pi radians different if you wanted to. That's absolutely fine for that question. This next question is all about the kinetic energy of simple harmonic motion, or an object that's undergoing simple harmonic motion. So it could be an oscillating mass, it could be an oscillating pendulum. It's important that it's mass because later on we are going to talk about spring constant and stuff, but it doesn't really matter for this point, okay? The first one is to work out the frequency of the oscillations, so we're going to have to work out the time period from the graph. Now, a lot of people will just see, oh, up, down, it must be this amount of time here. However, let me explain. Now, if we just take it as a pendulum, because I think it's easier to understand than a mass, you could do this with a mass as well. Imagine a pendulum goes from side to side, so it goes to there, and then it travels back to its original position. There are 2 times when it undergoes maximum kinetic energy. Time 1 is the first time it goes through the equilibrium point, so here. Time 2 is on its way back, so here. So for one time period, it goes through the equilibrium point twice, so it reaches maximum kinetic energy twice. So the time period is actually this spot here, when it's undergone 2 of those peaks and come back down to 0 kinetic energy. So when we're looking at the time period, we're looking for, what's that? That's 0.84, I reckon. So that's 0.84. So 1 divided by 0.84, and that's going to give us a little frequency of 1 divided by 0.84. Which is 1.19. They do give you a range for this one because it is reading off a graph, but that's what they want to figure out, is that it's 0.84 and then a final mark for doing 1 divided by that. Then we've got to sketch onto the figure a graph showing how potential energy of the mass varies with time during the first second, so only up to this point here. Now, potential energy, you've got to be careful when drawing graphs in physics. Treat it as if it's like a 2-mark written question. Take 2 minutes over it. Most people will know, or roughly, it's going to be the inverse. So when potential energy is highest, kinetic energy is lowest, and vice versa. However, imagine you're an examiner, imagine what the mark scheme is going to say. They're going to be really picky about the points, which point, because we know that kinetic energy plus potential energy is going to have to be constant throughout. So at any point on this graph, the potential energy and kinetic energy has to equal 0.1. So let's be really careful about it. Let's mark up where we're going to start. So we're going to start there. We're going to have another maximum at 0.42. So where's that, about there? And then another maximum 0.84 about there, and we don't have to worry about the other bit because it's 1 second. The other part they're going to check in the mark scheme is it does it when this is 0.05, does the potential energy also equal 0.05? So they should cross over halfway between 0.04 and 0.06. So you've got to be really careful with that. And then obviously do it in pencil. I'm doing it in pen just so that it's more obvious on the screen, no pressure. So you're passing through all the points you've just sketched out, and up down to, messed up there, to 0 seconds, okay? So the ideal here is be precise, okay? There's 1 mark for the shape, there's 1 mark for checking it, that each point it's roughly 0.05. They'll give you like plus or minus sort of a square, half a square, something like that for that question. Question 2 continues over here with a fairground ride, which if you use the Oxford textbook and other textbooks, they'll have a whole little lesson about fairground rides because they're really good examples of how simple harmonic motion works. So just to sort of picture it here, you've got a pivot, so the ride is pivoting around this point here. There's 3 riders strapped in a harness. You've got information about the cables, the height, etc., which will all be important later. The information we'll look at down here is also important because it tells us you've got a time period of 14 seconds. It says they're 1 meter off the ground. We've got that there already. And it says speeds of, quote, up to 120 kilometers an hour. So the first question is, treat it as a simple pendulum. That's our clue, what equation to use. Show the distance between the pivot and the center of mass is 49 meters. The clue is in the fact they say a simple pendulum because this is an approximation, this equation, and it works for simple pendulum where we're not considering the mass of the string or things like that. We're asked to work out the distance between them. So basically, we'll show the distance between them. We're asked to prove that it's about 49 meters. So that's going to be L. So we have to do a little bit of rearranging to get L by itself. So if I square everything, I've got 2 squared equals 4 pi squared times by, now I've got L and G out of the brackets. And to find what L is itself, I'm going to get G over to this side. So I've got T squared times G all over 4 pi squared is going to equal the length of the pendulum. So the time period we know, everything else we know. If we plug our values in, so I've got L equals 14 squared times 9.81 over 4 pi squared. You're going to get an answer of 48.7, which rounds to 49. So that's absolutely fine for a show question here. Over on the other side, we've got a little bit of circular motion to have a look at. In this question, it says the riders and the harness have a total mass of 280 kilograms. Calculate the tension in each cable at the lowest point of the ride, assuming the riders pass through this point at this speed here, and assume they have negligible mass, etc. at this point. So a couple of things to do here. First one, if you see units like this, you should think, right, I've got to convert straight away. So let's just get that out of the way first. So their speed is not 120 meters per second, it's kilometers per hour. So to convert it to meters per second, we do times by 1,000 to get it into meters, and we divide by 60 times 60, or 3,600, to get it into seconds, because currently we can't use that equation as it is. So if you do that, you'll find it equals 33.3 meters per second. Then we can go about using it. So if you imagine this whole thing kind of going in a big circle, so we've got circular motion going on here. At the bottom, so this part of the ride here, we need to be able to label the forces acting on it. So I'm going to do it on this diagram here, even though the question's over here. If we've got tension, that's going to act upwards in each cable. So tension, tension, and then there are 4 cables. So imagine there's 2 extra ones there. Then we've got the mass times by the G, so the weight of the people going downwards. Because they're going in circular motion, we know the resultant force is going to be towards the center of the circle. So that's Fc. We know that centripetal force is equal to mv squared over r. So therefore, resolving forces, we know that the centripetal force must be provided by tension, then you subtract the weight of the people. So we have mv squared over r equals t minus mg. We're asked to find tension, so what we're going to do is just add on mg to this side of the equation and get rid of it here so we can calculate what T is. So to find what T is, let's do mg, so 280 times g, then plus 280 again. I guess you could factorize that out, couldn't you? I run out of room here, 33.3 squared, that's the speed, and divided by r. Now r, the radius, is going to be the thing we've just worked out basically. So r here is 49 because you've worked that out earlier. That's the distance between the pivot and the center mass of the people, not this bit here. That's different. That's from there to the ground. So if you do all that, you should get answer. I'm really running out of room here. So you got this comes to 6,337, and then add on mg. You're going to find the whole thing is going to be 9.083 times 10 to the 3. I've really not left enough room here. Because it says tension in each cable, there are 4 steel cables. So you just divide that by 4 to get your final answer, 2.27 times 10 to the power 3. And that's 4 marks, which I think is about right for that question. Next, we're going to use this value here, finally, to show the maximum speed stated is exaggerated. So the maximum speed, it says, is 120 kilometers an hour or 33.3 meters per second. So we're basically got to find a way of finding out the actual speed of the people in the ride and see how it compares to 33.3. And they actually tell us it's exaggerated, so we're expecting to be a bit lower than that. Now, as the people come back down, and we're ignoring like air resistance and things like that, as they come back down, all their gravitational potential energy is going to be converted into kinetic energy. So we can just do a little bit of energy sort of comparison and go back comparing them. Or I guess you could use SUVAT as well. It's all the same thing, isn't it? So I'm going to do energy comparisons. So gravitational turns to kinetic. We can cancel the m's. If we're looking for V, this rearranges to get the 2 on that side, square root the whole thing, root 2gh. Which G is 9.81, H we're using this here, is not the length of the pendulum, it's 45 for this one. So 2 times 9.81 times by 45, and that's going to give us 29.7 meters per second. And we always get a mark at the end just for sort of doing a statement of like, were they right or wrong or not. So this is 120 kilometers per hour, in meters per second, and 29.7 is less than 33.3. So like they're right or it's an exaggerated claim. These kind of conclusions are way more important when it doesn't tell you whether it's right or not. They might say find out if it's exaggerated or something like that, and that would definitely be more important to do there. Next one, we're talking about kinetic energy again. It says the riders lose 50% of the energy of their oscillation during each half oscillation. After one swing, the speed as they pass the lowest point is 20 meters per second. That's kind of photocopied a bit weirdly there. Calculate the speed of the riders when they pass the lowest point, traveling in the same direction after two further complete oscillations. So, because we've done earlier in the question a kinetic energy time graph of this, we've learned that after one whole oscillation, the kinetic energy is going to be a maximum twice. So after two oscillations, so after two whole swings, we're going to have four maximum kinetic energies. So two oscillations, that's going to be equals 4 times by kinetic energy maximum, or when it reaches its maximum. Okay, so basically we've got to figure out it loses 50% 4 times. But what does it start off with? Well, first of all, we've got to figure out what it is at the beginning and then go from there. I think you can do it ratios wise as well. I'm just going to work out the start. I think that's potentially the easiest way of doing it. It tells us that the first lowest point is 20 meters per second. Bear in mind, we said the maximum speed up here was 29.7. However, they're losing energy now due to air resistance, so we know that's not actually true. That's just the maximum it could be. So therefore, initially we say kinetic energy equals half times by the mass of the people, so 280 kilograms still, times by 20 squared, which equals 56000. Then what we say is, because we worked out it's 4 lots of kinetic energy being maximum, so therefore it's 4 lots of it losing 50%. So we start off with 5600, and then we just say it loses, I don't know, half 4 times, or 0.5 times 0.5 to the power 4, which is the same thing as 1/16, you could also say. So you plug those values in and we get a kinetic energy go down, and I'm running out of room again because that's going to go down to 3,500. And maybe ratios might have been easier with this case. But anyway, now we've got new kinetic energy, so 3500 equals half, and then the mass 280 kilograms times by the new speed we've got to work out. Go off the screen slightly there. So down here. So if we do 3500 divided by half 280 equals v squared, and then square root the whole thing to find v, should find it comes out to be 5 meters per second. Like I said, the ratios might be easier in hindsight. If you're happy doing ratios, that's fine, but that's how the whole maths of that question would work. In this question, we've got another sort of fairground, circus, acrobat-y type of question, which exam setters seem to love for this topic. So we've got an acrobat this time with 2 people looking very, very dangerous on a platform with a motor that kind of swings around like this. This is from above, so it swings around in a circle, a bit like that. We've given them mass. We're told they're suspended from ropes attached to opposite ends, so like this diagram here, and they move at a constant speed in a horizontal circle on opposite sides of the pole, so sort of going like this round, or from the top. So the period of rotation they give us is 5.2 seconds. It tells us they're 5 meters below the platform, as mentioned here, and that's the angle of the ropes. So we've got to show the linear speed, so that's v, so not omega, is about 4.5 meters per second. So for linear speed, we either need to know the angular speed and the radius, or we can just do distance over time, which it basically works out as the same thing. So what we're going to do is do the angular speed, so times by the radius, which is 2 pi over t times by the radius, which is basically the same thing as saying the diameter, the circumference divided by time, so you could also do it that way. So the main thing here is to work out the radius, because the rest of it is simple. We've got t given to us, and that's not going to be enough for 2 marks, just a simple calculation like that. So how do we work out the radius? We've got to do a little bit of trigonometry. So if we treat one of these triangles kind of separately, we know that the thing is 5 meters vertically. We know this angle here is 28.5 degrees. So the radius we're looking for, the distance they are from the center, and don't forget we've got to bear in mind that 2 meters thing there as well. We've got to do a bit of trigonometry to work it out. So here we've got the adjacent, we're trying to look for the opposite. We don't know anything about the hypotenuse, so we've got to use tan. So tan theta equals what we're trying to find divided by our adjacent, which is 5. And we know what theta is, so we can just work out our opposite is going to be equal to tan 28.5 plus 5 meters, and that gives us 2.714, etc. However, that's not the full radius. Remember I mentioned this bit here. What we've got to do is consider that's at the center. The point at which it's orbiting around is right in the middle of that. So we've got to add on a 1 because it's half of 2 meters here. So we add 1, so that gives us 3.71. Now, this is quite a lot of 2 marks actually, isn't it? Now we know that, everything else is easy though, because I can just go back here, say 2 pi over the time, which is 5.2, and then just times the whole thing by 3.71, and you'll get, for the linear speed, it rounds to 5, so 5.49 meters per second. Don't forget to put your number to more sig figs than they've given you to show it to, just to make sure you guarantee that second mark. Next, we're going to use the angle again to work out the tension for the acrobats. So I'm going to draw that triangle again. This time, instead of distances on each side, we're going to consider the forces that are acting. So if this is the acrobat person out here, the angle's the same, so 28.5. So we're no longer talking about distances, so I can't write 5 in there. We're just going to be talking about forces acting. So we're looking for the force that acts in this direction, which is going to be the tension acting on the rope. The only thing we know is their weight. So we know the weight of the person is going to be 85 times by g, so 9.81. So we can use this to figure out, even though it doesn't seem obvious at first, because if we draw a slightly different triangle, which might help visualize it a bit better, if I draw this triangle here, so basically the sort of the other bit of the rectangle, the person here, if we work out this force, then we can use that to work out what the T is there. So if I draw T here, if I say they're going to have mg going downwards, therefore the side that's going upwards, because they're not moving they're not moving vertically, it says they're moving round and then just going horizontal motion round and round, they're not going up or down. So therefore in that sense they're in equilibrium. So essentially we can then say that this is going to be equal to mg, or equal to 85 times 9.81. So in our triangle then, this becomes 28.5, just because I've redrawn it. If you're happy doing this way, that's totally fine. Might be a bit easier to do that, to be honest. Let's then consider, so trying to find the hypotenuse. So we've got the adjacent over here, so that's mg in that direction. So therefore we're going to do cos of the angle equals the adjacent over t, which is hypotenuse. And then to find t, we're going to do the mg, so that's going to be 85 times 9.81, all divided by cos of the angle, so cos of 28.5. If we do all that, we're going to get 948.8, that is, which is the tension. Or we should probably give it to 2 sig figs here, so 950, because that's 2 sig figs earlier in the question. Yep. Cool. Right, this question, those of you who are good at maths, actually, that last bit. Those of you who are confident in maths would have found that bit relatively straightforward. Sometimes people struggle with the more wordy side of explaining things in physics, especially with a question like this, where we're asked to discuss the consequences, so what happens for the forces acting on the pole when one acrobat has a much greater mass than the other. So let's consider what would happen if that was the case. If one of the masses of the acrobats increases, so mg goes up, overall there's going to be a bigger vertical force, or sort of force pulling the pole down, because the mass has increased. So mass going down, that's increased, so weight goes down. So there are some easy marks to get, and there are about 3 different ways the mark scheme says of approaching this question. I'm going to show you the way I think is a bit easier. So you'd say something like the increased mass of the acrobat is going to increase the weight. So that increases the weight, you can say downwards, but that's just an obvious mark, which is quite nice. That's then going to increase the tension. So if you imagine when we worked out tension earlier, we had the mass of the person was pretty important. We're working out the tension, so that increases the tension in that cable, or in that cable next to that acrobat who's got increased mass. And then we could describe that there's going to be, because of that, we know centripetal force, as we said earlier, is mv squared over r. So there's going to be changed centripetal force because there's going to be a different mass. So it's enough to just say it changes here. So changes centripetal force, on that acrobat. And like we said earlier, so there's going to be a vertical like resultant force on the pole. Because the question asks about the pole, and so we're going to be specific, we're going to say vertically. So horizontally, it doesn't change, but we're talking about vertical. We're just talking about this. Tension will be higher, so there'll be compressive forces, you could say, on the pole, and that'd be enough for your 3 marks here. You could also talk about moments. You could talk about forces, the sort of turning force on each acrobat as well. The last question we're going to do is this question here. I'm only going to do this bit of the question because it's the one that relates to centripetal force, and that's what this video is all about. It is part of this question. Now, if you've seen it before, it's one with chevrons on it and cars, stopping distance and things like that. So I'm going to leave it on the screen because I'm going to use a couple of values from it, but I'm only going through this bit here. And I think it's one of the neatest derivations in physics. I really like it. This question is 4 marks. It doesn't say on the question, but yeah, we're going to get 4 marks for this question. However, I've seen it come up as a multiple choice question before, which is really, really horrible, but hey, these things happen. So the situation is a car going around a bend on a motorway. However, the bend is sloped, so it's not horizontal. The idea is so that the car is less likely to slide out when traveling at high speed. Given the radius of the curve and the angle of the slope, and we're actually given the forces, which is quite nice. Sometimes they could ask you to figure that out yourself. So you've got the weight of the car going downwards, and you notice the normal force, or the reaction force, is no longer vertical. It is a slight angle. That's because this is always going to be perpendicular to the slope, so perpendicular to the slope rather than always sort of vertical. So the question is to suggest an appropriate advisory speed. So basically, how fast can you go before coming off is essentially what they're after here. So we're going to use this diagram mainly, and we're going to use the figure from here to work out what this speed is. And like I said, it's 4 marks, so it's quite a meaty little derivation, but stick with me because I really think it's worth it. So what we're going to do is consider this force acting upwards here. I'm going to redraw it up here. And if I was to consider this force N, I can sort of break it into 2 component vectors. I could say it can break it into vertical and horizontal components, where this angle here is not 50, 5 degrees. So we're going to treat each one separately. So let's do the vertical one first. So the vertical component, so this is going to be our adjacent, so that's going to be cos. So we're going to have N cos 5 degrees, or cos theta, but cos 5 degrees is fine here. Now, if you consider that force going upwards here, because it's in vertical equilibrium, it's not moving sort of up and down, it's going at constant speed, that's going to be equal to the weight of the car. So we can then say, and I'm going to do all the workings here just because I haven't got much room down here, I'm going to say N cos 5 degrees is going to be equal to mg. So mg is going to be, actually, I think from memory, I actually don't need to write down m, even though they give it to us. I actually don't think we need it for this bit of the calculation, which is one of the neat things about this. Okay, so that's calculation 1. Next, we're going to consider horizontal forces. So this is the slightly tricky bit. Because the car is traveling in a circle, there is centripetal force acting in this direction towards the center of the circle. So from this car's point of view, it's going in this direction. So horizontally, FC is going that way. So what we can then say is we can resolve the horizontal component of n and say that is going to be, so n sine theta going the other way, or sine 5 degrees, and that's going to be equal to FC, the centripetal force. Now, we're not considering friction here. That would obviously be playing an effect as well, but we don't need to worry about that. So we've now got n sine 5 degrees is equal to, and we're not just going to say centripetal force, we're going to say that is equal to mv squared over r, because that's the equation of centripetal force. And now we have expression 2. What we're going to do with those 2 expressions is to divide them. So I'm going to divide 2 by 1. I'm going to do it up here so I've got room. So dividing 2 by 1 for reasons that are going to be obvious in a second. So we're going to have n sine 5 degrees. I'm going to do the whole thing, not just one side or another. We're going to divide the whole thing. That's going to be divided by, I should do it properly. Sorry, I'm in GCSE mode here. Divide by n cos 5 degrees equals mg. So dividing the whole thing. So I know it looks a bit messy, but stick with it. We're going to have the two m's cancel out, which is quite nice. We have the two n's cancel out, which is quite nice. And we're then going to have u divide, so sine over cos. Theta is always going to be tan theta. So therefore, this whole expression on this side then becomes tan theta. So I'm just going to go over to this side of the page, just because there's more room. Very, very messy, this page. So we're going to have tan 5 degrees can be equal to, so what I've got left on the right hand side is v squared over r all over g. So that can be neatened up quite nicely to be equal to v squared over rg. Next, we're after the speed, so the advisory speed. So we just need to rearrange this. Again, sorry, I'm going to be horrendously messy here. V squared equals tan 5 degrees times by r, which is 200 meters, times by g, which is 9.81. And let's see if we got close to the actual final answer. So tan 5 times 200 times 9.81, which gives us 170. God, I got scared then. Right, the v squared equals 171.65. So therefore v is going to be equal to square root of that. And if you do square root that, he says, hopefully, 13.1 meters per second, which sounds a bit reasonable. That's a bit faster than a sprinter if you think about it. So it's roughly, it can be the speed of a car. There you go. Right, that's the end of our simple harmonic motion and circular motion. If you found that useful, please drop it a like and let me know if you want me to do a specific topic next. And thank you for watching.